Okay, we're going to start with a review from last time of the fact that categories and comonoids are the same thing. So the idea was if you have a category, so here's a little picture of a category that might be familiar to some people. It's got two objects and two non-identity arrows. It's the index and category for graphs, if you know what that means. But what polynomial would this be, or what polynomial comonoid would it be? This, since it has two objects, will have two sum-ins. And the first one will have y to the power of the number of morphisms coming out of it, of which there are 3, 1, 2, and the identity. And this one will have the number of morphisms coming out of it, which is 1. So if you wanted to, you could use the online encyclopedia of integer sequences and write down oh, this is the polynomial, you could write this down 3, 1 and start classifying all of the categories you know as just they're generating functions. But of course, the category is not, maybe it's not completely obvious, but Nelson mentioned last time, the category is not completely determined by this polynomial. It's this polynomial together with a certain map from y cubed plus y to y, one that when you run around and you see what happens, how positions get sent to directions, picks out the identities, the identity here and the identity here in both cases, and a map from y cubed plus y to it compose itself. And if you write out what this composition is, it might take you a little while to write it all the way out because you have to cube this thing, and then you have to add one more copy of this thing. There's a lot of copies, and what's going on there? Well, what's going on there is basically that every position here is going to tell you all the information about all of its codomains and composites and stuff. That'll all be contained in this thing. And so, for example, another category with the same, so I'm not going to do that out, but here's another category with the same underlying polynomial. It has one morphism from something to itself called f, and f composed f is f. So you could have this little tiny monoid there and another object there, and they'd have the same polynomial, but they're very different categories. And in general, you can have completely different categories with the same polynomial. One thing you'll know is that they'll have the same number of objects and that something else is the same, but mainly just the morphisms out and the morphisms out are the same.
Sorry, David, what are the three morphisms coming out of the object on the left?
Good question. Let's say f cubed is f. So we have identity, f, and f squared. Thanks for the fix, Nelson. Okay, so here's another category, the commutative square. It's a favorite category of category theorists. What polynomial would it be? It would be y to the fourth, because this one has 4 morphisms coming out of it. This one, wait a minute, wait, 1, 2, the identity and the diagonal, that's 4. And this one has the identity and that morphism. And this one has the identity and that morphism. And this one has just the identity. And somehow, if you look at this, it almost looks familiar, like from algebra class in middle school or high school or whatever. But why does it look familiar? Well, it's actually y squared plus y, tensor itself. It's almost like something squared. It almost looks like something squared, but it's tensor square. And so y squared plus y, that's this category. I mean, in other words, note that this category has that underlying polynomial. And the fact that this one is this one times itself, like the shape of this is actually a square, the shape of this is a single line segment, the fact that this one tensor itself is this one, that is not a coincidence. We'll see that either this time or next time. Let me give you a couple more. Here's 0, 1, 2, ... Let's call this category n greater than, because the objects are the natural numbers, and the morphism is, there's a morphism from I to j if I is greater than or equal to j. But then there's also this one, n less than, and that's the exact opposite category. And I want to show you that in categories, like the ones we're thinking of, like the way we are representing them as comonoids, opposites are kind of weird. They're not as natural as they normally are in category theory. So what is the polynomial for this one? Well, it'll have as objects natural numbers. I'll call it n. But the morphisms out of 0, there's only one. And there's two morphisms out of 1. One that stays where it is, and one that subtracts 1. And there are 2 out of 2. One that stays where it is, one that subtracts 1, and one that subtracts 2. So, oops, so it's this. It's this polynomial there. You could write that as, I mean, well, there's lots of different ways to write that. And what is the, this is a polynomial. The comonoid structure would tell you a map from this thing to y, would tell you like what are the identities. And the identities is like how many we're going to subtract. So if we were at 3, we could subtract 0, 1, 2, or 3 and land at some codomain. And the other one would tell us, yeah, the delta, sorry. So we said a comonoid is a map, is a C, a map C to Y, and a map from C to C composed C. And this one tells us all about identities. This is what Nelson told us about last time. This one tells us all about codomains and composites. Okay. So somehow the data of a map from this thing to y would tell us that the identities we're calling 0. And the fact, like if we gave this map from this polynomial to it compose itself, somehow that would tell us. And if we wanted to say how, we would start drawing these diagrams and stuff, which we'll do in a little bit later. We would start tracing them out and see what they said. And when we read it out, we would see that subtracting I and then subtracting j more is the same as subtracting I plus j in total. So that's what this one would be. It's like, it's this polynomial here. So it's kind of like y plus y squared plus y cubed. That's this. This one, on the other hand, again, although it has the same number of objects, the number of maps out is always infinity. So this is just ny to the n, a very different polynomial. So category and its opposite do not have nearly the same polynomials, and you can't just look at one and derive the other. You have to know the whole comonoid structure of this one to get the whole comonoid structure of this one. Okay. Let me give one more example of a category. So let X be a space. So you might think of a metric space or a topological space. And for every little x in X, let C XX denote the following: the set of all D phi, where, or P, I don't know, P, where D is a real number greater than or equal to 0, and P is a function that, or is a continuous map from 0D to X. So what is that saying? These are supposed to be the curves in X starting at X. So if X was some space like this, with a hole in the middle or something, it doesn't matter, and here's a little x in it, then one of these C's, an element of this thing, would be some length, like 5, and a curve, a map from 0, 5 to X. That little curve there. Maybe I should call it C for curve. Okay. Okay, so there's a great category whose objects are the points in X. and whose morphisms out are all curves in x starting at x. And how does this work? The identity is the curve where d is 0. And there's a unique one. Oh, sorry, c from 0d to x such that c of 0 equals little x. Okay, so that's that. We take the identity to be the curve of length 0, of which there's only one. And then we take the codomain to be wherever d went under the curve. And we take composites to take, if we have a curve of length d that ends somewhere, and we have a curve of length e that ends somewhere else, we compose them to get a curve of length d plus e. And it's not very, it's like, well, why did you tell me the polynomial? This is just a picture of this category as a polynomial. I mean, all the data, this is already a category, and me writing as a polynomial doesn't help. I just wanted to say, polynomials are pretty general things, and you can, even though you get an entire, we get an entire space kind of represented in terms of its category. Its category of paths. And I think mainly the reason I'm saying this is because we'll come back to it later. So, any questions? Well, I don't know. Are there any questions from the audience, Nelson?
No, but you're frozen, so what are you trying to say?
We good?
I don't know, you can just keep going. Yeah,
Oh, good. Okay, we're back. So, in part 2 of today's talk, we'll talk about co-algebras, and we'll show that those are functors, like C co-algebras are functors from C to set. Okay, and now this equality is really an equivalence, not exactly an equality. But these two categories, the category of C coalgebras and the category of C co-presheaves, they're called, are equivalent categories. And so we'll explain that. So what did you say?
Okay.
Be a comonoid in poly. And C, the corresponding category. Oh, well, I guess I already said this. There is equivalence. I guess I'm writing a theorem now. There is an equivalence C coalgebras, which I have not defined yet, but I will, and functors. I guess I just said this. Functors from C to set. Okay, so how does this work? First, what is a coalgebra? A C, we have this comonoid, a coalgebra on it is one, a set S. This would be called the carrier. From S to C of S. Now remember, a set S can be thought of as a polynomial, and when you take C of S, if you take a polynomial and apply it to S, that's the same thing as P composed S. So sometimes it's more convenient just to write this symbol so we don't have parentheses that already have a symbol. Okay, so it's this stuff. This would be called a C coalgebra. But it has to, since C has this extra structure, we should ask that this map, omega, or whatever we call it, should also have this coalgebra. It should also have some extra structure. And that is, we know how to go from S to C composed S, but we also know how to apply epsilon. And we can apply it to this factor and leave this factor alone, and we get Y composed S. And Y of S, or Y composed S, is just S. So these are the same, and we ask this to commute. And we ask another one to commute too, that if we went to C composed S via omega, I apologize if we use a different symbol in the book. I forgot to look that up. Actually, you don't happen to know offhand, do you? Okay. Okay, if we do delta composed S over here, delta is the structure of the co-multiplication. Or we could do that, or we could do C and then omega again. And we want that to commute. And so what I want to read off is what this tells us. I want to use polyboxes again to say what this is telling us, and then give you a hint as to how you get the corresponding functor from C to set. So we have this function from S. S is S y to the 0. So it's like we have nothing there. So we have this function from S to C composed S. And this is omega. Okay, so let's give some notation for omega. Given a little s in here, I'm going to write absolute value of s to denote where it goes in C. And then given some morphism in C with domain S, I'm going to write s dot f for the element of S. So S is in C of 1. So the absolute value of S is an object, and S dot f is a new element of S. And that's going to be the notation we use for omega. And now we're ready to see with that notation, what these two things mean. So the first one says, if you start with S, and you go into this thing, C composed S, but then you use identity, that should be the same thing as going from S to itself like that. So we start with little s here. We take its absolute value. In C, we take the identity on that thing, and then we apply it to S, and we get S dot id. And so if we read off what this says, it says that starting from any S, we get that S dot id is S. So we've got this set. Every element of the set gets mapped to a single object in C, and we know how to take morphisms out of that object and get new elements of S. But when we apply that construction to the identity on anything, we get back our S. So that's axiom 1. And then axiom 2, coming from this, says what? It says, well, I guess I'll put it here and then copy the axiom above. So it says something about the following shape. We're going to take something here. We're going to go down, and then we're going to put it through this whole rigmarole. And then we're going to see what it says about what goes on here, here, and here, and here. But there's nothing that can happen here because this is S. All right, so what is all this rigmarole, as I'm calling it, I guess? Well, it's these polybox pictures, and I'm supposed to do omega. That's nothing, that's nothing. There's S, there's C, and there's omega. And then we're supposed to do, I don't know, let's do this one be C composed omega. So we're supposed to just copy this data. So that's identity there on C. And here's C again. And here's S. And this one's there. Let's see. Sorry, oops, wrong button. This goes here, and this is omega again. Okay, so that picture is supposed to be the same as doing omega, no data, no data, no data. then doing delta, and that's C's version of how you get codomains and composites, and then go up by identity on S. Like that. So you can see here S, C composed S, C composed S, C composed S, omega, omega, C composed omega, and delta composed S. Okay. So that's all the stuff we're supposed to write. And then what does it say? It says for any little s we pick, we can take its absolute value and then copy it. And that should be the same thing as taking s, taking its absolute value, and then delta copies it. Nelson told us that last time. Okay, so no data there. And then somebody comes and picks a morphism in C. And we could either copy it back and then take s dot f. That was our notation for what we do in omega. And then take its absolute value. Or we could just take the codomain of f, because that's what C thinks we should do here. And so this tells us that s dot f, so for all f, s dot f is cod f. So here f is in C bracket. Okay, don't need to worry about this too much. I'll write these out, and then I'll tell you what they mean in a second. And the last thing is if someone picks a G here, coming out of that codomain, then this guy says we're supposed to take s dot f dot G. And I know this is hard to read, but I'll copy it there. And so we have G also. And this one says we are supposed to take f composed G. We're supposed to take s dot that thing, and we're supposed to just copy it. So we get that s dot, I guess this might be number 3. But we're getting 2 and 3 from the same spot, from this diagram here. So it says that s dot f dot G is s dot f G. And now we're ready to say what a coalgebra is. A coalgebra, we've determined, is a set S, and for every element of S, an element of C called the absolute value, I guess we're notating that way, and a way to take any map out of that object in C and get a new element of S. And it has the following properties. When we apply the identity to S, we get S. When we apply a map and see where it goes, see what its absolute value is, we get cod of F. And 3, this condition here. If we take S dot F and then we dot it with G. So it's kind of like we have the name of S in C. S is like getting this object in C. And then for every outgoing map of that object in C, we have an operation on S. And that operation sends identities to identities. It works well with codomains. Like when we take the name of the object in S in C, we get codomain, s dot f. And it works well with composites. OK, so now finally, let me tell you what this is about. So I've told you what a C coalgebra is. It's a set S with this way of classifying its objects, its elements, and a way of acting on those. And so why would that be a functor from C to set? How would you go from one to the other? I'll just write it really small here, I guess. So how do I get a functor from C to set? Get this given S. How do I get it? Well, I'll call this thing W. W of some little I. If you have some object in C, what set do you send it to? Send it to the set of all S in S, such that the absolute value of S is I. So we've got this category, and we've got, I don't know what we've got. We've got some category down here. We've got all these objects, and some of them map to this guy, and some of them map to this guy, and some of them map to this guy. And so we take our functor from C to set to take every object of C to all the elements of S that map to it. And then if I have F taking I to I prime in C, and I have S in W of I, okay, I need to get an S prime in W of I prime. So how do I do it? Well, I have an element F in C bracket S. I shouldn't have gone it so low, I guess. I have some F outgoing from that object in C. So I can apply it. S dot F. And that's a new element of S. And that's what I needed. So what I'm saying is to get this functor, it's pretty easy. For every object I in C, just look at all the S's that went to it. And for every morphism in C, just apply that morphism to any object that went to it and get an object that went to it. So it's just kind of following your nose once you have, I guess, once you have the data of omega. And these things make sure that this really is a functor. So I'll leave that to you to think about. If you're interested in proving it, that there really is an equivalence, I think there's enough information there to do that. But the point is, I mean, why am I saying this? Because I think it's interesting that categories are comonoids, and then interesting things you do with comonoids give you interesting things you do with categories. Like one of the most interesting things people do with a small category is they look at functors from it to set. Those give you things like databases if you're interested in that sort of thing, and they give you things like sheaves if you're interested in that sort of thing. So this very common thing to do. Okay, so that's that. So now I wanted to talk about the third of these, and that is just kind of a fun thing that I didn't know before that one of the students from our class told us about, namely that for any P and Q in Poly, there is a new polynomial that I'm going to denote PQ, oops, QP. And for any R, an isomorphism. Poly maps from PQ, what? PQ to R are the same thing as polymaps from P to R composed Q. And of course, we see a lot of these with comonoids, right? So we have maps from C to C composed C, so we could always like move things around and stuff. This is maybe older than this, but the person I attribute it to, because I don't know the whole theory, the whole history, is Josh Myers, who's a student in taking this class. So he showed that this is true, and I think it's really neat, and so I wanted to talk about it and also put it in with the rest of our story here. But so it's an adjoint to this thing. What's its formula? PQ is the sum over the positions in P, has the exact same positions as P, but the morphisms are Q as a polynomial applied to P of I. And so that's the formula. So I'm not going to prove that this is true, but I just want to tell you some examples. So examples. For any sets A and B, well, you can think of sets as polynomials that are constant polynomials, and AB is it's the sum over I in A of y to the q, which is b, applied to something. But b is constant, so b applied to something is just b. So this is ay to the b. And what that means is that this notation, although Josh came up with this concept, I just gave it some notation. And the notation I picked is the one that matches how David Jasmeyers and I and other people denote lenses. So, so this is a lens. It's a monomial. So the monomials have this structure. For example, SS is sy to the s, right? Just by copying and pasting. So a map from sy to the s to some p is what we call a dynamical system. But now we know that that's the same thing by this formula here as a map from S to P composed S. And this is what people normally call a P coalgebra. And you might remember we talked about C coalgebras over here. These are sometimes called Lambeck style. In Lambeck style, P is just a functor. And we're looking at coalgebras for that functor. They're just a set with a map from S, with a map from S to P of S. In kind of Eilenberg-Moore style, a coalgebra would be on a comonad like this one, or a comonoid. And then you would have these extra conditions. So that's kind of a confusion of notation or terminology. But the point is that a lot of people have studied, like Bart Jacobs and other people have studied dynamical systems in the way that we might see them as coalgebras for a polynomial functor. And we've been looking at it this way. And I like both ways of thinking about it. They both have nice things that you can do that are harder to do in the other one. We're going to start moving into thinking them more this way, I think, in the course. But the point is that they're equivalent by this thing that, by this co-closure here. OK, let me give a few more examples. Or no, let me just give you something you can do. So here's some facts. Well, these are like some laws, some natural maps, I guess. So you take this thing. This is a very common thing to do throughout category theory. You take an adjunction like this. This is called an adjunction. And you plug in for R, you plug this thing in. And when you do that, a neat thing happens because you get an identity morphism here, which gives you a canonical morphism here. So what I'm saying is if you plug in QP for R, you get that poly maps from QP to QP, of which there is an identity. There's a special one in there, so like we get one for sure. No matter what Q and P are, we know there's a map from QP to QP. And therefore, we know there's a map from P to P composed QP. OK, so what I want to do, there's another thing we could do. We could put R composed Q in for P here, and then get R composed Q here and get a special map like that. I'm not going to need that, but you could do it. It's a good thing to do. And so but the point is I get a special map here, and I want to use that for something. And that is, for any polynomial P, I get a map from PP to Y. Why? Because a map from PP to anything would be the same thing as a map from P to that thing composed P. And I, of course, have a map from P to P. And that gives me a map from PP to Y. Did I do it backwards? No. OK. So I get a map from PP to Y. But I also get a map from PP. I also get a map from PP to PP compose itself. And how do I get this one? Well, to get this one, it suffices to get a map from P to PP composed P. Why? Because that's the definition here. I can always take this guy and rotate it. Ooh, I forgot to show you the cool notation for it. Oh, well. I'll do that in a second. Yeah. Maybe I will, or maybe I won't do it in a second. So if I had one of these, that would be enough, but I do because of this trick I had over there. My identity here gives me a special map from P to P composed QP for any P and Q. So I get a special map from P to P composed PP. I did that right? P to P composed PP. I guess so. What did I do? QP to QP. P to P. No, I did it wrong. Okay, I did it wrong. Let's look over here again. It says that we're supposed to, given this map from QP to R, and this thing is our special R, we're supposed to get a map from P to R composed Q, but this is our special R. Okay. There we go. That's what I was expecting. And so we get a map from P to QP composed P. That's all I'm saying here. The special identity here, the identity map from QP to QP, gives us a map from P to QP composed P. And now we do this in a special case.
One of those
Oh, sorry. Which one? This one? Yeah. Thank you, Nelson. But luckily it doesn't matter here. We get a map from P. Oh, right. No, that was right. We want this thing. But we get this thing because, right, there it is right there. But now we can take this thing, copy that, and get another one from P to PP composed P. So if we call this special map, I don't know, eta or something, then we get eta here, and then PP composed eta. So the point is, we get a map from P to this big thing by just doing this twice, and therefore we get a map from PP to it compose itself. And if you have a map from some polynomial to y, and the same polynomial to itself compose itself, then it stands to reason that if those are at least somewhat natural things, if you got them from some natural way and not just arbitrarily, they're probably going to be a comonoid. And indeed they are. You can go check the conditions of what it means to be a comonoid, and these give you a comonoid structure on PP for any polynomial P. So for any polynomial P, PP gives the structure. These two things give PP the structure of a comonoid, meaning it's a category. So for any polynomial in the world, we get a category. And that, I think that it's just such a cool fact. So what category is it? For any polynomial like y cubed plus 4y plus 7, we get a category. What category do we get? And we know how to get the category because we know how to get the comonoid. And I'm not going to take you through all the steps, but I just want to tell you what you do. Well, I guess I'll take you through some of the steps. So first of all, PP of 1, if PP is a category, then PP of 1 is its objects. And we said that PP of 1 is P of 1. So now we know the category we're going to get has the same number of positions as P. PP's objects are P's positions. But what is what are the maps out? There's a lot of brackets around, but let's suppose we had an object I, a position, or an object. Well, this is this thing. It's P applied to P of I. So it's P applied to P of I. I'm just reading it off. And that is a position in P times the product over the directions there of the directions in I. And so here's what I'll tell you. I'll just tell you the category. Hom in PP from I to I prime is Hom in set. Sorry, this is the same thing as another object in P of 1 and a set map. For every one of these, we get one of these. So it's a set map, a function from P bracket I prime to P bracket I. So it's like you have this polynomial. It's got this many positions, and then in every thing it has this many directions. I don't know, here's y cubed plus 2y squared plus 1. And it says that we're going to get a category with 4 objects. And the 4 objects, the maps between this object and itself is the functions from 3 to 3. And the morphisms from this object to this object are the functions from 2 to 3. And the morphisms between this object and this object are the functions between 2 and 2. And the morphisms between this object, and any other object are the morphisms from empty set to that object, or whatever it is. So what I'm saying is this is the full category of set, or maybe, I guess, set up, spanned by the P bracket I's. So it's the full subcategory of set, actually set up, spanned by the sets 3, 2, 2, and 0. For example, we know that sy to the s as a comonoid was the contractible groupoid on S, but now what we're seeing it as is the full subcategory of set with P of 1 many objects. So it's got S many object, S. So ob equals S, and Hom from one S to another S is a set map, a function from 0 to 0, because these polynomials, S as a polynomial has all of its P bracket I's empty set. It's a constant polynomial. So we recover what we knew before, that there's exactly one function from S to S prime, or one morphism from S to S prime for every S and S prime in big S. Anyway, so I think this is a really neat. One last thing to say is, like, what do you get for list? So where list is 1 plus y squared plus y cubed. This thing is fin set op. The category of finite sets and morphisms between them. Because you get every finite, like basically, yeah, you get all the finite sets here. And this is equivalent. Okay. Any questions on that? All righty. So now that was just kind of fun. I think it's really nice. And I want to go back to categories and cofunctors. So a cofunctor is a weird, it is not a contravariant functor. It's not a certain kind of functor. It is a map of comonoids. So let's just, so number 4, what are maps of comonoids viewed as maps of categories? So remember, a comonoid in Poly is a category, but a map of I have two markers open. But a map of comonoids may or may not be a functor, and we're going to find out it is not a functor. It's something else. So a map of comonoids, definition, let C and D be comonoids in Poly, or in any category, in any monoidal category. I'm using the same notation for C's epsilon and D's epsilon, and C's delta and D's delta. Hopefully that won't be confusing. I don't think it will be. A morphism between them is a function, is a morphism. So we're going to say in Poly, but everything I'm going to say would be true in any monoidal category. Is a morphism C to D in Poly such that one, well, two things commute. One is you do C, and then you go to D, and then you go to Y with epsilon in either case, and this should commute. And the other one is if you go from C to D, and then you delta both sides, and then you use phi, monoidal product phi, that should commute. And so what we want to do is say, this is a map of comonoids. I want to know what it means for categories. But before I tell you what it means for categories, I just want to trace out what it means set theoretically. Okay. So what it means is we're going to get this map phi from C to D. And so given any object in C, we're getting some phi of I, an object of D. And then given any morphism out of that thing, I don't know, G, D bracket that thing, we get phi upper sharp G coming out of I. So we have two categories, C and D, and the first thing we know is that a mapping of this new sort sends objects of C to objects of D, and then given any morphism out of that object in D, we get a morphism out of the original object in C. And the question is, what rules should this satisfy? And we know it satisfies these rules, but we don't know what those mean for categories yet. And so let's trace them out and see what they say. The first one says that if you go from C to D, and then you apply epsilon, you take the identities in D, that's the same thing as taking identities directly in C. So I, phi of I, identity sub phi of I, phi sharp of identity sub phi of I id. And what does that tell us? It tells us rule 1. Id I, so for all I, for any object, we shoot it forward, we take the identity and we pull it back, we get that thing is id. So id sub phi of I and id sub I. I wrote it tiny because it's just you're just supposed to remember, I'm able to pull morphisms back and I pull identities back to identities. Okay, what else do we get? We also get that if I go from C to D by phi, and then I duplicate, meaning I take codomains and composites, delta. Now that's the same thing as starting in C, taking its codomains and composites, C, 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 delta, and then shooting both halves over to D. Okay, let's read it off. So we're going to get some more axioms here about cofunctors. Cofunctors take objects in C to objects in D and pull morphisms back. And we know they pull identities back to identities. But what else do we know? We know that for any I in C of 1, and then some phi things probably. So I, phi of I, phi of I. I know what delta does. What delta does is it copies here, takes anything we want to do here and takes the codomain, and then takes anything we want to do here and takes the composite. So we take some morphism G, and we go here, we get cod G. And now we're about to write a fact. So we say I is an object of C, I is itself, and then we get phi of I, and that's the same. We take our G, we take phi sharp of it, and we get cod G, cod phi sharp G. And there's not enough room here for you to read it, but I'm going to copy it up here big enough for you to read. And here's what we learned. We learned that cod, so if we have a G in phi of 1, phi of I, we learned that cod of G, so we took an object, we mapped it forward, we took a morphism out, and we know that its codomain is the same thing as if we see where the codomain of the map-backed thing went. Right? We take our morphism, we pull it back to C, we take its codomain, and we push it forward, and that's the codomain. And lastly, we know one more thing. If we take H, we do G composed H, and we do phi sharp I, G composed H, that's the same as phi sharp H, and then okay, so number 3, so let's say we had an H in what? H is in, oops. H is in D bracket cod of G. So what we know now, our third axiom, is that phi upper sharp I, if we pull back G composed H, that's the same thing as pulling back G and composing it with phi sharp H. So we pull back identities to identities, we push forward codomains to codomains, we pull back composites to composites. And that is what a cofunctor is. A cofunctor is a functor from one category to another. What is it? A cofunctor from one category to another sends objects of C to objects of D, tells you how to pull morphisms out of that object in D, back to that object in C, and doing so preserves identities, codomains, and composites. That's a cofunctor. So let me give you some examples. What time is it? 59? Oh, I think we usually stop at this time. So what I'll do is I will start again next time with where we are now. I'll remind you what a cofunctor is, and then I'll define the category So next time, review cofunctors, and then give examples, and then some other stuff, like talk about co-free comonoids. So, okay, thanks. Oh, thanks, Nelson. Okay.